Hello and welcome back to the latest video in a series in which I've been building experiments from this book, Charles Platt's Make Electronics, the third edition. And today we've actually come to the very last proper experiment in the book. And in the previous video, the book introduced us to the wonderful world of digital electronics using microcontrollers. But that experiment, the final outcome was just a flashing LED, not the most exciting outcome we might have hoped for. And as that outcome can be fairly easily achieved using quite a simple analog circuit, probably not the best demonstration of the capabilities and the benefits of microcontrollers. Nevertheless, we had to start small. And now we've got that groundwork out of the way, we can start to explore those capabilities in a bit more detail. And to that end, the book has us build a new version of the electronic dice we built back in experiment 23. Only this time we'll be using the microcontroller instead of discrete logic chips. So let's get going with that.
For this project, the book has us make a single die rather than the pair of dice we had in experiment 23. Now, as we used the classic Arduino Uno for the experiment in the previous video, for this one I'm going to use the Arduino Nano Every. One tip if you're using this board: when you mount it on the breadboard, it will of course be straddling the center channel, so the pins on either side of the board are isolated from each other. Now, you won't be able to get it exactly central, but get it as close as you can so you've got 2 holes on one side and 3 holes on the other to connect external components to the pins. The other thing you should do is put it right at the end of the board, starting at row 1 on the breadboard, and orient it so the USB connector is at the edge. There are 2 good reasons for doing this. One is so that it's easier to plug a USB cable in, and the other is that, unlike the Uno, this board is too tiny for the pins to be labelled, so you will need to count them to make sure you're connecting wires to the right pin. And that's going to be a lot easier if you start at row 1 on the breadboard. Now, before you build any of the external circuitry, it's worth opening the Arduino IDE and connecting your board, just to check that everything is working okay. So I've connected a new Nano Every, and as you can see, as soon as I have power, I'm seeing the onboard LED is blinking. And that tells me that this board has a pre-installed program, and it's basically a variant of the classic blink sketch we built in the last experiment. Now, it appears the Nano Every is not yet supported by the Cloud IDE, so for this experiment I'm using the installable IDE on a Windows machine. In this IDE you'll need to select the board from the drop-down list in the command bar. If you've not connected this type of board before, you'll also be prompted to install the required support files. With that done, the first thing I suggest you do is upload an empty sketch, which should just have an empty setup function and an empty loop function and nothing else. This ensures when you start connecting external circuitry, if you power the board up, you're not going to have any issues with an old program interacting with your hardware in a way you didn't intend, and potentially damaging either the microcontroller or an external component. So here you can see the breadboard set up with the LEDs and current limiting resistors and a single push button switch. That's all you need from the original analog circuit. The microcontroller is going to do the work that the logic chips did in that circuit. Another tip, where you're using consecutive pins, as we are here, is to use an appropriately sized ribbon cable rather than individual wires to connect the pins to the hardware, and then just separate each wire as much as you need to at one end where they connect to the external circuit. And that really helps to keep things tidy. But whichever wiring method you use though, Make sure the development board is not powered while you are connecting and disconnecting external components. You'll want to carefully check that you have everything wired correctly before applying power. By the way, you won't need any other external power source like a battery. This circuit will be entirely powered through the USB connection to the development board. So that's the circuit built, but for it to do anything useful, of course, we need to do some programming. So I've copied the sketch from the book and uploaded it to the board. Let's see it working, and then we can take a detailed look at the code. So here, when I push the button, we get an effect to simulate the die rolling, and after a couple of seconds it stops and shows the final face value. And each time I release and press the button, we see the same sequence ending with a different random value. Let's look at the code that is needed to achieve this functionality. In the circuit we built in the previous video, there was no need to store any values. We simply set a pin to either be high or low. Because the functionality of this circuit is a little more complex though, we will need to store some values. We do this using variables. A variable is a named location in memory that we can use to store a value. These lines at the top of the file are variable declarations. In a variable declaration, we give the variable a name and optionally a value separated by a single equal symbol. So here, for example, we are setting the variable called spots to be equal to 0. But what's this strange int thing at the start of each of these declarations? This is the variable's type. Now C++ is what's known as a strongly typed language, which means that objects, like variables, must have a precise type. In this case, we've declared the type to be int. That's short for integer, which is a whole number. It means we can only store whole numbers in this variable. And if we try to store anything else in it now, like a character or a number with a fractional part, then the compiler will show an error when we try to compile the sketch. Now this might seem like an unnecessary restriction, but it's actually a discipline that will save you from a lot of functional errors as your sketches get more complex. Note that functions also have a type, because some functions return values. In front of the setup function here, you can see the word void. The void type means that this function does not return a value. But down here, you can see we call a built-in function called millis. If we look that up in the Arduino documentation, you can see that this function returns the number of milliseconds that have elapsed since the program started running. And if I look down at the return section here, you can see that this has a return type of unsigned long. Long is basically a large whole number, and unsigned means that it's always a positive number. Now we use the term variable because the value held in these locations can vary. It can be changed as long as what we change it to is the same type. So here you can see we're adding the number returned by millis to 2000, and we're storing that value in the variable ignore. This statement is a variable assignment. Note the difference between a declaration and an assignment. In a declaration, you state the type and the name, and optionally assign an initial value. In an assignment, you don't need to restate the type. You merely put the name and an equal symbol and then the value you want to assign to the variable. As you can see, the value you assign can be just a simple value, as in the declaration statements, or it can be calculated with an expression, in this case a simple addition. Whenever you assign a variable, any value that the variable held previously is replaced with the new value. So how do we make use of the value in a variable? Well, we can simply refer to the variable in an expression. For example, down here we can see the variable spots is used in several expressions. Whenever we use the name of a variable like that, the current value of the variable will be inserted into the expression when that line of code is executed. So if spots contained, let's say, 3 at the point this line was executed, then the value 3 would be inserted in that expression. Now, if you watched the previous video, all our code in that experiment was placed inside either the setup or the loop function. But here, these variable declarations are at the top of the file, outside of both those functions. This is because of something called variable scope. This means that where you declare a variable determines where that variable is available. For example, if we declared ignore inside the setup function, it would have function scope. It would only exist while setup was being executed. Outside of that function, ignore would not exist. So if we tried to use it inside the loop function, for example, this would generate an error. However, in this case, you can see that ignore is used in both the setup and the loop functions. This is why we declare it outside both functions. When we do this with a variable, it has global scope. That means once it is declared, it always exists while the sketch is running, and it can be used in all functions within the sketch. One quick side note here. As you learn more about programming, you will undoubtedly come across programmers who will tell you that global variables are a very bad thing and you should avoid them at all costs. This is because in larger and more complex programs, global variables can cause hard to track errors. So while this is not bad advice, the Arduino development environment has been set up to make things easy for those new to programming. And unfortunately, global variables often cannot be avoided if you use this language and this IDE without employing a system of variable passing between functions, which is frankly too advanced to go into here. So my advice, while you're learning to program the Arduino boards, is to always look for opportunities to reduce the number of global variables you use, but don't get too hung up about it if you can't eliminate them entirely. In this sketch, for example, ignore is used in both functions, so it has to be a global variable. But if we survey the code, we can see that outpin and spots are only used in the loop function. So we could remove these global declarations here and modify the statements where they are first assigned in loop to also be declarations. And on the subject of the loop function, let's have a look at what's going on there. Here is another statement you've not seen before. This is a for loop. It's a construct that will execute a block of code repeatedly for a set number of times. The code it will execute is placed within curly brackets. How many times the loop is executed is dependent on the 3 statements separated by semicolons here. This first statement is executed once only before the first loop. The most common thing to do with this statement is set up a counter variable. Here we're setting the variable outpin to be the number of the first pin to which we've attached an LED. By the way, in the book this is pin 1, but mine here starts with 3 because I'm using the Arduino Nano and I've used pins 3 to 6 to drive the LEDs. The second statement is executed at the start of each loop, and the loop will only be executed if this statement evaluates as true. It's commonly used to check if the counter variable has reached a particular value. For example, here we're checking that it's less than 7, because once we've reached 7, we've gone past the pins attached to the LEDs. Once the variable does reach 7, this statement will no longer be true and the loop will stop executing, and execution will then continue with the first statement after the for loop. The final statement is executed at the end of each loop. It's commonly used to update the counter variable. For example, here we use a new operator, plus plus. This simply adds 1 to the outpin variable. So the combined effect of all three of these statements is that outpin will initially be set to 3 and it will count up by 1 at the end of each loop until it reaches 7, at which point looping will cease. A useful thing about for loops is that the counter variable you use is available within the body of the loop. In this loop, we're using it in a digital write statement to set the corresponding pin to a low state. That means we'll loop through all the pins connected to LEDs and set them all to low. In effect, this loop is turning off all the LEDs, and we need to do that at the start of the loop function, because otherwise we'd very soon end up with all the LEDs on and they would just stay on. Here we're picking a random number for the spots on the die. Random is a very useful built-in function that will return a random integer between the first argument and one less than the second argument. So in this case, it will return a number between 1 and 6. We then use that value to determine which LED should be lit. We do this with a series of if statements. An if statement is how we make decisions in the sketch. Like a for statement, an if statement executes the code within curly brackets, but that code will only be executed if the statement is true. For example, here the code will only be executed if the value in spots is 6. Note the double equals symbol. This is what we use when we want to check that something is equal to something else. A common mistake is to mix up a single equals symbol, which is used for assignment, with a double equals symbol, which is used for checking equality. The problem is, it's not an error to use a single equals here. But what will happen if you do is that it will assign 6 to spots and it will always evaluate as true. That's a horrible error to find, the sort that could have you scratching your head for a while trying to work out what's going on. So do watch out for this one. The way I used to remember it is with a simple rhyme. To assign, you put just 1 in line, but for equal, add a sequel. You can see as well as equality, we can test for one value being greater or indeed less than another. Now this expression here is a little bit different to the others. This double line symbol means logical OR. It means this expression will evaluate as true if spots is equal to 1 or 3 or 5. Taken together, these 4 if statements will ensure that the correct pips on the face of the die are lit for the randomly chosen number. The delay statement here is one you encountered in the last experiment. This one is here just to slow down the rate at which the loop function executes, so that you can see the tumbling effect of the die numbers changing. Without this statement, they would change so rapidly they would all just appear to be flickering. Okay, it's time now to turn our attention to the button and how we use that to trigger the die roll. You might recall from our earlier experiments using buttons with integrated circuits that we could use them in one of 2 ways. If we wanted the IC pin to normally be low and for the button to set it high, we'd connect a pull-down resistor between the pin and ground, and the button would connect the pin to the positive supply. Conversely, if we wanted the pin to normally be high and for the button to set it low, we'd connect a pull-up resistor between the pin and the positive supply, and the button would connect the pin to ground. The microcontroller in the Arduino has the ability to connect each pin internally to either a pull-up or pull-down resistor, so we don't have to add one in our external circuit. All we need to do is tell it which to use. In this case, our button connects the pin to ground, so we need to specify that this pin is an input pin connected to a pull-up resistor. Note that as I'm using a Nano every rather than an Uno, I've connected my button to pin 2, not pin 0 as shown in the book. The other pin mode function calls in setup are just setting up the pins connected to the LEDs, and you should be familiar with those if you watched the previous video. Note this statement at the end of setup that's adding 2000 to the result of calling millis. Effectively, this is setting ignore to the value millis will have in 2 seconds time. To see the relevance of that, we need to go to the end of the loop function. And here we have another if statement. This is checking for two things. One is whether millis is returning a value that is greater than the one in ignore. In other words, has 2 seconds passed since ignore was last set. We use this to ensure that we get 2 seconds of the die rolling effect before showing the next stable face value. The second thing it checks is whether the input pin connected to the button is low. Remember, because we used a pull-up resistor that normally holds the pin high, a low value indicates the button is pushed. This double ampersand symbol here is a logical AND. That means that both conditions need to be true for the entire expression to be true. When both these things are true, the code in the curly brackets is executed, and this just calls a function check button. You may recall in the previous episode I said that the setup and loop functions were the only functions we're required to write, but we could optionally create other functions. Well, check button is an example of that, and here we have the definition for that function. The first thing you'll see here is a brief delay. Why is that there? Well, if you recall, back in experiment 22, we learned about the need to debounce switches to remove rapid, spurious connections and disconnections as the switch transitions from one stable state to another. The two calls to the delay function here are what we use to effectively debounce the switch. Next, you'll see an instance of another type of loop, the while loop. This works like a for loop, except that the code between the curly brackets is executed while the expression in parentheses is true. But wait a moment, did the author forget to put in the code to be executed? Well, no. When you just want to wait for a certain condition to be true, it's common to use a while statement like this with an empty body. Effectively, this statement executes continually while the button is pressed. In other words, it's waiting for us to release the button. Once we do, we get another debounce delay, then another while loop. This one executes continually while the button is not pushed. In other words, it waits for us to push the button again. Effectively, this series of statements holds the circuit in a stable state so we can read the pips on the die, until we release and then push the button again to start another roll. Finally, at the end, we reset ignore so that we get another 2 seconds of roll effect. So that's the code. Let's end with one more look at it in action, and hopefully now you can match what's happening with the code.
Well, I hope you found that useful. Now, as I mentioned earlier, this was, sadly, the very last proper experiment in the book. But there is one more chapter in which the author introduces us to a few more popular microcontrollers and development boards. And in the next video, I will also be showing those boards. But additionally, I will be announcing some bonus content. So if you want to find out what that is, please do join me. See you then.